So in this session we will summarize some of the important concept of ordinary differential equation. We will start with the boundary value problem or particular case of the boundary value problem, which is called self adjoint boundary value problem, and there are some special type boundary condition. Based on this boundary condition we will classify the boundary value problem, and further we will discuss some of the properties on these boundary value problem, and further we will go for the questions. So let's start with the definitions. So define a self adjoint boundary value problems. So the differential equation d over dx with a naught x y dash plus some, or let's define in other notation, dy dx into derivative of px y dash plus q of x plus lambda time r of x into y equal to 0, assuming that x belonging to closed interval a b, and also assuming that this px is continuous and differentiable function, and qx rx are continuous function on the interval ab, and where lambda is, and this lambda is fixed constant. And let's denote this differential equation with the equation 1. Then there are some boundary conditions. So given equation is a homogeneous second order linear differential equation, and let's define some of the boundary conditions. Say a naught y at a and a1 y dash at a is equal to 0, and b naught y at b plus b1 y dash at b is equal to 0, assuming that a naught square plus a1 square is non-zero, that is at least one of the either a naught or a1 is non-zero, and similarly b naught square plus b1 square is not equal to 0, that is at least one of the either b naught or b1 is non-zero. So this differential equation with the second condition is called self adjoint boundary value problem, and if p of x is greater than 0 for every x belongs to closed interval ab, and Rx is also greater than 0 for all x belongs to closed interval ab, then the differential equation 1 with second boundary condition is called a regular or regular boundary value problem, or also we say it is SLP, Sturm-Liouville problem. So this first differential equation with this second boundary condition is called either regular boundary value problem or Sturm-Liouville problem. And if we will define another boundary condition, say y of a is equal to y at b and y dash at a is equal to y dash at b, say this is third, then the first differential equation with respect to certain condition on p and r with the third conditions is called periodic boundary value problem. That is, if p a is same as p of b and px is greater than 0 for all x belonging to closed interval ab, and Rx is greater than 0 for all x belongs to closed interval AB, then this first differential equation, then 1 with respect to third boundary condition is called periodic boundary value problem. So we are defining two type boundary value problem, regular boundary value problem and periodic boundary value problem. There is another classification of this differential equation. If Px is 0 for some point on AB, or basically Px is 0 at A or B, then this equation with this second boundary condition is called singular boundary value problem. We will not go further for singular boundary value problem. So we are just focusing on regular boundary value problem or periodic boundary value problem. Based on these classification, there are some properties on this boundary value problem, and based on this property there are always question in CSIR NET JRF exam. So this is the two classes of boundary value problem. Let's further define the what are the eigenvalues and what are the eigenfunction for the boundary value problem. So the meaning of eigenvalue or eigenfunction is nothing, it is, so the meaning of eigenvalue or eigenfunction is nothing, it is the value of lambda for which this differential equation has a non-trivial solution, that is a non-zero solution, then that lambda is called eigenvalue and corresponding non-zero solution is called eigenfunction of the boundary value problem. So let's define the lambda or the value of lambda for which one with second or third boundary condition has non-trivial solution is called an eigenvalue. And corresponding non-trivial solution is called eigenfunction. So this is the definition for eigenvalue and eigenfunction. That is the values of lambda for which this equation has non-trivial solution is called eigenvalue and corresponding non-trivial solution is called eigenfunction. And based on the classification of the boundary value problem, there are some properties on eigenvalue and respective eigenfunctions. For example, if given boundary value problem is regular boundary value problem, then number of linearly independent eigenfunction corresponding to any eigenvalue always 1. That is, the dimension of eigenspace is always 1. And in the case of periodic boundary value problem, there are some eigenvalue such that corresponding eigenfunction are corresponding eigenspaces are 2 dimension, or there are some eigenvalue corresponding eigenspaces are 1 dimension. So let's summarize the what are the properties or what are the in general properties for regular boundary value problem or periodic boundary value problem. So start with the general property for both of the equation. So if given problem is regular or periodic boundary value problem, in both of the cases, first is the eigenvalues are always real numbers. Second is the eigenvectors corresponding to distinct eigenvalue are linearly independent. That is, if lambda 1 and lambda 2 are distinct eigenvalue and y1 and y2 are corresponding eigenfunction, then y1 and y2 must be linearly independent. Third property is the eigenfunctions or eigenvectors corresponding to distinct eigenvalue are orthogonal. That is, the eigenfunction corresponding to distinct eigenvalue are orthogonal, and meaning of orthogonal is if lambda 1 not equal to lambda 2 are two eigenvalues and y1 and y2 are corresponding eigenfunction, then integral a to b rx y1x y2x d of x must be 0. This Rx is called weight function of the differential equation. So that is, these y1 and y2 are orthogonal vector with respect to this weight function Rx. So this is the third property for either regular boundary value problem or periodic boundary value problem. See, eigenvalues are real and eigenvector corresponding to distinct eigenvalue are always linearly independent, and the eigenvector corresponding to distinct eigenvalue are orthogonal vectors. So these are three main properties for eigenvalues. And fourth property is, this is also for in general regular or periodic boundary value problem. If A is lambda belongs to R such that differential equation has non-trivial solution. That is, A is set of all eigenvalues of the differential equation. Then A is always infinite set. That is, every regular or boundary value problem has infinite number of eigenvalue, or there exists infinite lambda belongs to R such that this differential equation has non-trivial solution. Second is, the elements of A can be arranged into strictly increasing sequence lambda 1, lambda 2, lambda 3 and so on, lambda n, such that the sequence lambda n diverges to infinity as n tends to infinity. That is, the every element of this set can be arranged into a strictly increasing sequence, and this sequence must be diverge to infinity as n tends to infinity. And from this property we can directly imply that A is always bounded below and unbounded above. So this is the next property for regular or periodic boundary value problem. Similarly, every element of this set is in this strictly increasing sequence implies this set has no limit point. That is, every element of this set is an isolated point. So, every element of A is an isolated point. So, this is the next property, and if every element of A is isolated point implies this set is nowhere dense. The next property is A dash is phi, that is derived set of A is phi and A is nowhere dense. So, this is the next property, and since set of isolated point is countable and A is infinite, so A must be countably infinite set. So, next property is A is countably infinite set. So, these are the main properties for this regular or periodic boundary value problem. So, the set of eigenvalue is always countably infinite and the set of eigenvalue does not contain any limit point, and set of eigenvalue so is always bounded below, unbounded above, and main property is the set of eigenvalue can be arranged into strictly increasing sequence which diverges to infinity as n tends to infinity. And we are assuming that this sign is always positive sign. If there is minus sign, we can replace lambda by minus of lambda, and further we will go for these properties. And based on this property, again we can continue with the some of the other properties. So, another property is there does not exist lambda naught belongs to R such that differential equation has non-trivial solution for every lambda greater than lambda naught. So, if we will assume that there exists lambda naught belongs to R such that this equation has non-trivial solution for every lambda greater than lambda naught, implies every lambda greater than lambda naught is an eigenvalue, implies there are uncountable number of eigenvalue, which is contradiction. So, there does not exist any lambda naught belongs to R such that this differential equation has non-trivial solution. Similarly, there does not exist lambda naught belongs to R such that differential equation has trivial solution, only trivial solution for all lambda greater than lambda naught. Again, if we will assume that there exists lambda naught belongs to R for which this equation has only trivial solution, implies the set of eigenvalue is bounded above, which is again contradiction since this set is always unbounded above and bounded below. And next property, there always exists lambda naught belongs to R such that the differential equation has only trivial solution for all lambda less than lambda naught. Since this set is bounded below, so you can take a least lambda naught for which this property holds. Next is, so these are three main property since set is bounded below and unbounded above. Again, the differential or the number of negative eigenvalue are always finite if exist, the negative eigenvalue may or may not exist. If exists, then that set must be finite. Since this set is bounded below and unbounded above, if there are infinite number of negative eigenvalue, then set of all those negative eigenvalue is bounded set, and we know that every infinite bounded set has a limit point. That implies this set A also has a limit point. Again, this is the contradiction. So there are always finitely or finite number of negative eigenvalue provided exists. So these are all properties of regular or regular or periodic boundary value problem. Further, we will go for the main properties of regular boundary value problem, and then we will discuss the properties of periodic boundary value problem. So let's start with the properties of a regular boundary value problem. So for regular boundary value problem or Sturm-Liouville problem, SLP. So assuming that the set of eigenvalue assuming the set A of eigenvalue is of the form lambda 1 less than lambda 2 less than lambda 3 less than lambda 4 and so on, less than lambda n and so on. And since we have write down the first property, the set of eigenvalue can be arranged into strictly increasing sequence. So we are assuming that this set can be arranged into this form, and this sequence lambda n diverges to plus infinity as n tends to infinity. So this is the arrangement of eigenvalue. Now next property is the dimension of eigenspace E lambda I always 1, that is the number of linearly independent eigenvector corresponding to any eigenvalue in regular boundary value problem or Sturm-Liouville problem is always 1. That is, if there are two eigenvector corresponding to an eigenvalue, they must be linearly dependent. Second main property is if yn x be an eigenvector, is an eigenvector or eigenfunction corresponding to lambda n, where lambda n is the eigenvalue which placed at nth position, then yn x has at most n minus 1 zeros in open interval AB. So that is corresponding to nth eigenvalue of the regular boundary value problem or Sturm-Liouville problem, the eigenfunction has not at most, it has exactly n minus 1 zeros in open interval AB. In closed interval there may be n zeros, there may be n plus 1 zeros, or there may be n minus 1 zeros. It will depend on boundary value, boundary conditions. So by this property corresponding to lambda 1, the eigenfunction does not have any zero since n equal to 1. Corresponding to lambda 2, every eigenfunction has exactly 1 zero in open interval AB. Corresponding to lambda 3, every eigenfunction has 2 zeros in open interval AB. Similarly, corresponding to lambda n, there is exactly n minus 1 zeros in open interval AB. So this is the main property, and since corresponding to lambda 1 the eigenfunction does not have any 0 in open interval AB, so this eigenfunction does not change its sign in open interval AB or closed interval AB. Similarly, corresponding to lambda 2, lambda 3, lambda 4, the eigenfunction has at least one 0, implies the eigenfunction corresponding to any eigenvalue which is either lambda 2, lambda 3, lambda 4, lambda n always change its sign in open interval AB. So, these two are the most important properties of regular boundary value problem or stream Lebesgue problem. So, what are these properties? Eigenfunction corresponding to least eigenvalue does not change its sign in closed interval AB or open interval AB. That is, either remain positive throughout or remain negative throughout. It will never intersect the x axis in the open interval or closed interval. And if yx is an eigenfunction corresponding to lambda k, where k is greater than 1, implies yx change its sign in closed interval AB or open interval AB. So, this will be the next property for the eigenfunction or sign of the eigenfunction. So, these are the main property for regular boundary value problem or stream Lebesgue problem. Since corresponding to least eigenvalue the eigenfunction does not change its sign, implies if there is eigenvalue which is lambda equal to 0 and corresponding eigenfunction does not change its sign, then there does not exist any negative eigenvalue. Since the least eigenvalue is only eigenvalue, corresponding eigenfunction does not change its sign. Similarly, if lambda equal to 0 is an eigenvalue and corresponding eigenfunction change its sign, then there must exist negative eigenvalue. So, based on these two property, we can find whether negative eigenvalue exists or not based on the 0 is an eigenvalue. So, next two property is for finding negative eigenvalues or existence of the negative eigenvalue. So, first one is if lambda equal to 0 is an eigenvalue and corresponding eigenfunction does not change its sign, implies there does not exist any negative eigenvalue. That is, all eigenvalue are non-negative. Similarly, if lambda equal to 0 is an eigenvalue and corresponding eigenfunction say yx change its sign, implies there must exist a negative eigenvalue. So these are the two property for verifying whether negative eigenvalues are exist or not, and all these are properties for regular boundary value problem or Sturm-Liouville problem. So further we will go for properties of periodic boundary value problem. So some of the main properties for periodic boundary value problem. So again, assuming that A be the set of all eigenvalue and given problem is periodic boundary value problem. So A is the set of all eigenvalue. Again, we can arrange the set of eigenvalue into strictly increasing order, say lambda naught, lambda 1, lambda 2, less than lambda 3, less than or equal to, less than lambda n, and so on. So the set of eigenvalue can be arranged into strictly increasing sequence, and we are taking some special note, lambda naught, for least eigenvalue. Then first property is the dimension of eigenspace E lambda naught is always 1. That is corresponding to least eigenvalue in a periodic boundary value problem. The dimension of eigenspace is always 1. That is, there are exactly one Li eigenvector corresponding to least eigenvalue, and dimension of E lambda k is always 2 for all k greater than or equal to 1. That is, other than least eigenvalue, the dimension of each eigenspace is greater than or equal to dimension is exactly 2 dimension. So these are two main property for periodic boundary value problem, and based on this property we can verify whether there exists negative eigenvalue or not, provided 0 is an eigenvalue. So how to verify negative eigenvalue exists or not for periodic boundary value problem? So if lambda equal to 0 is an eigenvalue and dimension of E lambda 0 is 1, that is lambda equal to 0 is the least eigenvalue. So this implies there does not exist any negative eigenvalue. So this one is the first property for existence of the negative eigenvalue in a periodic boundary value problem. Second is, if lambda equal to 0 is an eigenvalue and dimension of E lambda equal to 0 is 2 dimensions. That is, lambda equal to 0 is not least eigenvalue, it may be sum of the lambda 1, lambda 2, lambda 3, any lambda n. So there must exist at least one negative eigenvalue. So these are 4 property for periodic boundary value problem. So based on all these property, we can easily solve the question or theoretical question we can easily track by these all property, and further we will go for the questions based on these regular boundary value problem or periodic boundary value problem.